Assalamualaikum warahmatullahi wabarakatuh. Hello, we are from Group 4, which consists Rian Rifki and Riana Oktafianti, will bring material entitled Radiation Thermometry.
Radiation thermometry, optical pyrometry, radiation pyrometry, infrared pyrometry, and spectral or total radiation pyrometry are some of the methods of thermometry based on the measurement of thermal radiation, also called blackbody radiation. In radiation thermometry, in contrast to resistance thermometry, we make use of a well-established equation, the Planck radiation law, which relates thermodynamic temperature to the measured spatial radiance. The thermal radiation existing inside a closed cavity, blackbody radiation, depends only on the temperature of the walls and not all upon the shape or composition. Provided that the cavity dimensions are much larger than the wavelength of the thermal radiation. The radiation escaping from a small hole in the cavity is perturbed by the presence of the hole. The careful design, this perturbation can be made negligibly small, so that equilibrium blackbody radiation is available for measurement.
Radiation thermometry. Radiation thermometers, called pyrometers, were developed for measuring high temperatures greater than approximately 1100 degrees Celsius. And they have an advantage that they are non-contact thermometers. Optical pyrometers measure temperatures of objects by comparing the visible radiation from the hot object over a narrow wavelength band with the radiation from a standard, preferably using a photoelectric detector for measurement rather than the human eye. Correction for the emissivity of the surge must be made to determine the temperature. Total radiation pyrometer measures the whole spectrum of electromagnetic waves, including infrared radiated by the object, in order to determine the temperature. Total radiation pyrometers are less accurate than optical pyrometers, but can measure much lower temperatures, including the triple point of water. So much material about radiation thermometry that we can convey. Let's move on to the next material.
So, for the next subchapter, chapter 1.14, we will discuss about vapor pressure thermometry, and my partner Rihanna will explain to you first.
Saturation vapor pressure thermometry is commonly used for the measurement of temperature in the range between 0.3 and 5.2 Kelvin. Because of the sensitivity and convenience of this type of measurement, the thermometric substance is the vapor in equilibrium with the liquid of either of the two isotopes of helium, helium-3 and helium-4. Helium vapor pressure is the thermometric parameter because it depends only on a physical property of a pure element and can be reproduced at any time. It requires no interpolation device and it is relatively easy to measure with significant precision over much of the temperature range.
The range of practical usefulness of the helium for vapor pressure scale is from approximately 1.0 K, because of the small variation of pressure with temperature and complications due to superfluid behavior, to 5.2 K because the liquid doesn't exist above this temperature, or the critical point. The range for the helium-3 scale is from approximately 0.30 K because the pressure is inconveniently small to measure, to 3.32 K, or the critical point. So this is the end for this subchapter, And for the next subchapter will be explained by my partner Brianna. Thank you.
The next material that we will convey is about thermocouple.
The thermal electromotive force or EMF is generated at the point where wire A and wire B are joined. The two thermocouple wires are connected to copper wire located at the reference junction, which is maintained at the temperature of melting ice. A thermocouple is calibrated by measuring the thermal EMF at the test junction at various known temperatures. The reference junction being kept at 0 degrees Celsius. The results of such measurements on most thermocouples can usually be represented by a cubic equation as follows. Epsilon is equal to C0 plus C1 theta plus C2 theta square plus C3 theta cube, where epsilon is the thermal EMF and the constant C0, C1, C2, and C3 are different for each thermocouple. Within a restricted range of temperature, a quadratic equation is often sufficient. The temperature range of a thermocouple depends upon the material of which it's composed. The type key thermocouple made of a chromal wire, 90% of Ni and 10% of Gr, and an aluminum wire is made from 95% of Ni, 2% of Er, and 2% of Mn, and 1% of Si, has a temperature range of minus 270 to 1372 degrees Celsius.
The advantage of a thermocouple is it quite rapidly comes to thermal equilibrium with the system whose temperature is to be measured because it may be small. The EMF of the thermocouple is adaptable to electrical circuits, which monitor and control temperature in many industrial, commercial, and residential furnaces, ovens, and cooling units. The disadvantage as far as scientific temperature measurement is concerned is that the imprecision is about 0.2 Kelvin, which is 5 to 10 times larger than the imprecision of the platinum-resistant thermometer of higher temperature. Therefore, the thermocouple is no longer a standard thermometer used in the International Temperature Scale of 1990. Material about thermocouple is finished. So let's go to the next material.
So, for the next subchapter, chapter 1.16, it's about International Temperature Scale of 1990, or can be said as ITS 90. And my partner Rihanna will explain to you first. Thank you.
The International Committee of Weights and Measures is concerned with two temperature scales. The first is the theoretical thermodynamic scales, the second is, at any given time, the current practical temperature scale. The use of constant volume gas thermometer for routine calibration or for the usual measurement of thermodynamic temperature is impractical. In 1927, the first international practical temperature scale was adopted to provide the means for easy and rapid calibration of scientific and industrial instruments. The practical temperature scale was revised or amended in 1948, 1960, 1968, 1976, and 1990. The International Temperature Scale of 1990 or ITS-90 consists of a set of defining fixed point measures with the primary gas thermometer and a set of procedures for interpolation between the fixed point using secondary thermometers.
Although ITS-90 is not intended to supplant the Kelvin thermodynamic scale, it's constructed so as to provide a very close approximation to it. The differences between the practical temperature scale T90 and the Kelvin thermodynamic temperature scale T are within the limits of accuracy of measurement attained in 1990. The accurate measurement of temperature with a gas thermometer requires years of painstaking laboratory work and mathematical computation, and, when complete, becomes an international event. Such work is published in the journal Metrologia and eventually is listed in the tables of physical constants. The equilibrium state temperatures of a number of metals have been measured, and the results are tabulated in the following table.
The lower temperature limit of ITS-90 is 0.65 Kelvin. Below this temperature, the scale is undefined in terms of a standardized thermometer, but research continues in order to select a reference thermometer from competing instruments. Various intervals of temperature on ITS-90 and secondary thermometers are established as follows: from 0.65 to 5.0 Kelvin. Between 0.65 and 3.2 Kelvin, the ITS-90 is defined by the vapor pressure temperature relation of helium third, and between 1.25 and 2.178 Kelvin, or the A point, and between 2.178 and 5.0 Kelvin by the vapor pressure temperature relation of helium 4. From 3.0 to 24.5561 Kelvin, between 3.0 and 24.5561 Kelvin, the ITS-90 is defined by the helium third or helium fourth constant volume gas thermometer. Uh, from 13.8033 to 1234.3 sorry 1234.93 Kelvin, between 13.8033 and 1235 34.93 Kelvin, or minus 200 and 59.3467 to 961.78. The ITS-90 is defined by resistance ratios W times T of platinum resistance thermometers using the specific fixed point given in table 1.3, and by reference function and deviation function of resistance ratios between the fixed points. 11 subranges have been established to accommodate a variety of necessary measurements. Above 1234.93 Kelvin. At temperature about 1234.93 Kelvin, or 961.78 degrees Celsius, ITS-90 is defined by an optical pyrometer using the ratio of spectral concentration of the radiation of a black body as calculated using Planck's radiation law. Only one reference temperature is required for the pyrometers: the freezing point of gold, the freezing point of silver, or the freezing point of copper. Before ITS 90 was adopted, the thermocouple was the standardized thermometer for the upper temperatures. It was removed due to insufficient accuracy. The range of the platinum resistance thermometers has been extended upward to its present limit, and the optical pyrometers is the new standardized thermometer for the highest temperature. We've had enough for this material. Let's move on to the next slide.
And for the next subchapter 1.17, it's about Rankine and Fahrenheit temperature scales. And my partner Rihanna will explain to you first.
Ranking and Fahrenheit temperature scale. The temperature scale commonly used by engineers in United States are based on a unit interval of temperature equal to 5/9 the size of a unit interval of temperature on the Kelvin and Celsius scales. By definition, the Rankine scale, named after the English engineer, is an absolute scale. It's based solely on the temperature of the triple point of water. The Rankine scale, which just measures the word degree, is related to the Kelvin temperature scale by the equation T times R is 9/5 times T times K.
Fahrenheit scale, named after the German instrument Micah, is defined in relation to the Rankine scale by the equation theta degree F is equal to Tr minus 495.67. Thus, at the S point, where the Kelvin temperature is 273.15, the Rankine temperature is 9/5 times 273.15 is equal to 491.67 R. Hence, the Fahrenheit temperature is theta degree F is equal to Tr minus 495.67 is equal to 32 degree F. The Fahrenheit temperature is related to the Celsius temperature by the equation theta degree F is equal to 9/5 theta degree C plus 32.
Okay, that's all we can say. Sorry for the shortcomings. Wassalamualaikum warahmatullahi wabarakatuh.